Good morning. Thank you for the nice introduction. My name is Milos. I work for Ethereum Foundation. And as it was said, I will give a sneak peek of what the Ethereum roadmap is, what we are working on, and where this is all leading, or at least one of the directions. Okay, so just to know a bit more about my audience, who here never heard about statelessness, or who heard about statelessness but doesn't really know what it is, refers to, what it is about, or anything like that? So please raise your hand if you don't know what this talk is actually going to be about. Okay, some hands. And who here doesn't know what are Ethereum clients, or never heard about Ethereum clients, or doesn't know what even that is? Okay, so everybody at least somewhat familiar with Ethereum clients. But let's look a bit into more details about it anyway. So currently, if you discuss about Ethereum clients, they are divided mostly into 3 categories: archive nodes, full nodes, and light clients. And I will go into details about them. But let's see first what the Ethereum clients can do. And I'm mostly talking in the context of execution layer. There's also consensus layer and clients there. But for this talk, we mostly talk about the execution layer clients. So let's say what they can do. That is the column, that is the rows. And we have the main category that every blockchain needs to do is build new blocks. And we will see not all clients can do that. Another thing is we want nodes to, or clients to verify the blocks that are being built. We want to be able to create transactions, even if they're not building blocks, to maybe create transactions that will be sent to other blocks, to other clients to build them. Head state refers to accessing the state of the blockchain at the head of the chain, meaning if you want to know what is my current balance right now at the very head of the chain, or either a balance, or what tokens I own, etc. What is the price of the Ether asset on the Uniswap exchange, etc. So that all refers at the moment. And the historical state refers to what was my balance a year ago, or something like that. And that is, historical state refers to very crude access to that state. It doesn't even refers to, for example, if you want to answer a question, give me all transactions from my wallet. Like, that requires some processing and indexing data to be effectively accessible. Like, if you have all historical state, you can find that information, but it's usually not efficient. So you need additional pre-processing of the data. And I'm not even covering that because none of these clients actually support that kind of indexing natively. You need to build on top of it. And requirements is basically a base comparison between these clients and what they're offering. So the archive nodes, they can do all of this, but their requirements is depending on the implementation, because for each of these nodes, there are multiple implementations written in different programming languages by different teams. So it kind of like depends, but usually the requirements, if you want everything, you need around 10 terabytes of data, which is quite a lot if you just want to run it on your own machine. It's still manageable, but kind of quite a heavy requirements to run that. Full nodes are the more common type of nodes that people are running. They offer pretty much the same except access to historical data. It's maybe ironically they're called full nodes but not offering everything. Might be counterintuitive. The fact is that they actually store all the historical blocks. So they can create the historical state and give access to that, like, because they have all the blocks, but they don't have the state, historical state. They could technically recreate the state and give you what was your balance a year ago, but it would be very costly for them to do it. So they are full nodes because they have everything, that they can do everything, but some of the stuff, primarily the historical state, would be very expensive, so they just decide not to do it because it's too expensive operation and you should do something else if you need that. Light clients, well, there is no clear definition or requirements of what light client exactly is. There is some kind of consensus that when people talk about light clients, they talk about some kind of software that is not always running or always synced to the head, doesn't require a lot of storage. Like full nodes, they require less than 2 terabytes. That's usually used as a benchmark of how much they need. Light clients are expected to require significantly less, maybe in order of hundreds of megabytes or something like that. But there is no strong requirement of how they operate, what exactly functionality they provide, et cetera. And there are a couple of attempts of making them more user-friendly, et cetera. But it's quite difficult. And that's why we have something like this. They definitely cannot build blocks or verify blocks, because in order to do those at the moment, you need the entire state. An entire state is already 400 gigabytes of data or something like that, depends on the implementation. And light clients, by default, they are supposed to store significantly less. So they cannot do the first two things. The others, depends on how they're implemented. They can do some of it with certain trust assumptions, because even for the others, you need some kind of access to the state. And light clients maybe have them, or maybe they use some centralized entity to get them. Maybe they verify them, maybe don't verify them. So it's kind of questionable what they can do and how much trust assumptions you put there into doing the operations. And what is the goal? The goal is to make the light clients much better and much more efficient, basically not being able to need all the state to do certain functionalities as an Ethereum client. And that's where the statelessness comes in a roadmap of Ethereum where we are aiming at. So how would that look like? So first, main thing that we want to do is we want block verifiers that they don't need the entire state in order to verify the block. That's the first requirement. So we want everybody to be able to easily run a node and verify the blockchain without actually having the entire state. Second aspect is we probably still need block builders to have the entire state. This is a concept called weak statelessness. There is also another concept called strong statelessness, where even the block builders don't need to have the state. It's a bit more challenging, obviously, to do that, and requires more work. There's not so much research being done in this direction, so I will primarily be speaking in the direction of the weak statelessness, because that's where the most work and most research can be done so far. Okay, so what are the benefits of the statelessness? Well, if you can run the validators on much smaller machines, you have much better experience for validators. You can run it on either a laptop or maybe even a phone, or just like any random device. Like, it probably also doesn't have to be all the time online. If you're running a staking validator, then yes, it has to be. But if you just want to run a validator to just verify the blockchain, then you don't need to be online all the time, etc. You don't need to sync the state, because you don't need the state to begin with. That also helps with scalability, because it's much easier to run these kind of clients. When they are easier to run, then it's more decentralized, meaning everybody can run them. It allows a lot of new features that you can do on top of it, because it becomes, to enable statelessness, it allows making the proofs about the state much easier. That's what's requirement. We will come to that. It also helps with layer 1 and layer 2 interoperability, because it becomes easier to prove the state and all the transition, etc. So what is the main idea behind the statelessness? So if we have blocks, every block has certain fields, hash of the previous block, a time step, a state root, transactions, etc., many more. And what we want to do, in order to execute or verify one block, you need to execute transactions in that block. And to execute transactions in that block, you need some of the state that those transactions access. Currently, nodes have all the state, so they have everything that transaction could possibly need, and that's the only way to do it. With statelessness, you could have something that is called execution witness. The execution witness basically contains the state that is only needed for executing that block, and with the proof anchored to the state of the previous block. So if you have execution witness embedded within the block, it can have the state that is needed and the proof of the previous block that that state is a valid state, and then the block can execute that one block at a time with all the data is being there. They don't need any entire state to keep themselves. So what do I mean when I say state? I am talking about basically accounts, their balances, other parameters like nuances, smart contracts, like just the bytecode of the smart contracts, and also like what is stored in a smart contract, like storage of the smart contracts. Currently, the entire state is called in a structure called Merkle-Patricia tree. If you are doing Solidity or maybe some protocol development like that, you might have heard about it. And one of the properties of the structure is that any piece of content is provable relatively simply. Downside of it is that you can already do this with the Merkle-Patricia tree. The problem is if you want to prove the entire block, the proof of that entire block would be too big. Now, it depends on the average size, etc. There was some research. Technically, you can already do it, but the proof size would be too big to be practical in a real case, because all these block execution proofs would have to be transmitted to every node in the network, and that would be order or 2 orders of magnitude much bigger than what they are already doing. So it's just too big to be practical at the moment. So we need to make the proofs smaller. So what is the solution? We use snarks. That's the direction we are going. Snark stands for Succinct Non-Interactive Argument of Knowledge. It is related to the zero-knowledge technology. And what is the idea is that we need a new structure for the state. And that is where the current ongoing research is going. We have one approach called worklet trees with the EIP where it's spec'd out. It's been already done a couple of years. A lot of research been done into this. It has one downside that was known from the beginning, and that is that it's not a final state. Even since the beginning of working on the worklet trees, it was known that there will be another transition after the worklet trees. Reason for that is being worklet trees are known to be non-quantum secure. And we will know that eventually we need quantum security. But when the work was starting, there were no good quantum secure alternatives, and the work started in the direction. Recently, maybe in the last couple of months, there is being research going towards something called unified binary trees, which are quite similar in many aspects to the worklet trees, but they are quantum secure. So potentially, we could go directly to unified binary trees instead of going to worklet trees and then switching to something else. We can go directly, but the work being done on the unified binary trees is significantly less. So the research is not as far, but if we can go directly to that one, then we only need to change the state only one time. So there are some benefits on both directions, and there's ongoing research of how both of them would work. Again, cryptographic primitives for the worklet trees are way more stable, while the quantum secure primitives are also still in a research regardless of the statelessness context. They are also relatively new and maybe not as robust and not as researched as others. So there is a website, Statelessness FYI. You can scan the QR code, more information about the ongoing work, projects, research, etc. on this topic. OK, so let's see what the stateless clients actually gives us. This is the image from before. So once we have a stateless clients, what can they actually do? So they can basically just verify blocks. They cannot do anything else compared to light clients. So they can do everything light clients can do, which is not much, but they can very effectively verify the blocks. And that's where basically the main problem starts with stateless clients is they don't have a state. So they cannot do almost anything except verify blocks, and they're very good for that. It's already a good concept. But this is the Portal Network is a project that I'm working on within the Ethereum Foundation, and that's where it comes to the story. Everything about Portal Network take a bit of question mark, let's say, at the moment, because just yesterday was announced the big reorg within Ethereum Foundation, and the future of the Portal Network is a bit unclear at the moment. But if this doesn't happen to be a Portal Network, it might change to some similar project or protocol that will serve similar purpose. So have that in mind. OK, so the Portal Network is basically protocol adjacent to the mainnet or main Ethereum blockchain data. It's another decentralized. It provides decentralized access to the Ethereum state. What does that mean? Well, imagine archive node that has all of the data in one machine that I said is around 10 terabytes. Imagine that being spread around the peer-to-peer network, similar to other peer-to-peer networks, like, for example, torrent or something like that, where every bit of content is provable, belongs to the mainnet data, and you can access from other peers the content that you need about. You don't need to store everything yourself, but it's distributed on the network, and you can fetch it from there. So it's basically decentralized light access to Ethereum state, more like a decentralized archive node. And the execution clients already started integrating. It's part of the progress of EIP 4.4s, where basically, currently, as I said, the full nodes, they have the whole blockchain history. So they don't have the state of the entire history of the Ethereum blockchain, but they have all the blocks and all the transactions that ever happened. So they can execute those from the beginning if they really care about it. And the EIP 4.4s is basically something called history expiry, where execution clients want to delete some of that old content and not have it locally. And they're working towards integrating with the Portal network to use Portal network to get that information if they need it. So basically, instead of every full node storing the entire history of transactions, they're going to drop some of it and keep maybe 5%, maybe 10% of the whole history of the blockchain. And the rest, like if everybody keeps 5% or 10%, there is enough redundancy in that peer-to-peer network that everybody has access to all the data that they need. And they're working on integrating the Portal network in their clients. You can read more about Portal network on that website. OK, so what would potentially, so this was the previous chart. And now let's see with Portalnet client. So Portal client would basically provide all of this functionality in a trustless and decentralized manner. Of course, the check mark is a bit smaller with an asterisk because it's not going to be as efficient. When you have a peer-to-peer network, you will be able to access all of this data and have it locally and verifiably without any trust assumptions, but it's going to be slower than if you have all of the data yourself. The Portal network is designed such that you can decide how much you want to contribute. You can configure your client. I just want to contribute maybe 1 gigabyte or 10 gigabytes of data on my local hard disk, or I just want to store 5% of the old state, no matter how big that is. It will keep growing. So you can configure how much you want to contribute to the network, and you will have access to the entire state from other peers. Of course, it's going to be slower than if you have everything locally. So that's why, like, the user experience, if you want to use it for like a user-facing feature or something like that, it's not going to be as great, but you can have access to all of it. And because of that latency, it's not good for building blocks, for example, or some other latency-dependent operations. The Portal network wouldn't be a good solution for it, but everything it requires or allows either a small state or a bit longer latency, you can probably use it. And that is a solution. So if there is one takeaway from this entire talk, that would be that lightweight decentralized clients are on the way. They're being researched and in progress. And yeah, thank you. Any questions? There is a microphone.
Hello, I remember that last year at the ASP Belgrade, you provide us the 3-day meetup, the 3-day event for a presentation of the progress of Portal network. I remember that I also took part in that. But I wonder that besides the Portal network and the currently unified binary tree, do you have any? Do you know any more progress on the data structure optimization of Ethereum data storage, besides the Verco and the Portal network and the unified binary tree? Do you know any other progress?
As far as I'm aware, there is no other research or progress being done on the actual state and the structure, how the state is stored. I'm not aware of any other research other than what you said, worklet trees, unified binary trees. And Portal network doesn't really change the structure, it just changes how or introduces a new way of decentralizing and storing the state, so it doesn't really change the structure, just introduce the more decentralized way of doing it. There are other work on being done, but sort of unrelated stuff on indexing maybe the data and distributing the indexed data across the network, etc., so that, for example, even if you have access to the older state, you cannot effectively answer the question, give me all my previous transactions. Like you would need to go and iterate every block and try to find where are your transactions, or you would have to index them before and then have access to it. So having access or indexed data also helps with like a user experience for like a most basic queries. Like if you have a wallet, you want to know all your previous transactions, and that's not very easy to do. You have to do some kind of like indexing, etc. So there are projects being worked on doing that kind of stuff that is more like making the access to the data easier, but there was no other project I know being researched that actually affects how the data is stored on the Ethereum mainnet, as far as I know.
Okay, thanks. And I hope to know more research grant opportunities provided by either Ethereum Foundation or the Portal Network program to boost the research of the data structure or data storage optimization, further optimization. And I hope to keep contact with you on the Portal Network Discord. Okay.
Okay. Any other questions?
So for the vertical trees, that, as you already just said, actually, we have a problem with the post-quantum security, right? So, and you said like that there are just two ways for, or the two research paths for the statelessness. I just wonder, like, why didn't we try to find another post-quantum security commitment style for just achieving the statelessness? For example, we have like lattice-based post-quantum security commitments that we can prove the whole tree with, to like prove the correctness of the execution and the access. But I couldn't like find reason to not trying to find a like lattice-based commitment.
So I'm not actively working on this, so I might not provide the best and correct answer, but I will tell you to my understanding at least. The unified binary trees are designed such that you can actually use any hash function inside the string. Like it doesn't really matter what it is, as long as it has certain properties that we want, like it's easy to prove, it's easy to aggregate and create multi-proofs, etc., etc. I think the one being considered the most at the moment, at least by the researcher doing that, is Poseidon. The risk of some of the new hashing function that might be better, more performant, is they didn't pass the scrutiny of time. So a lot of them, and even Poseidon is questionable, is that they weren't basically, they weren't known for too long. The research community didn't have enough time to test them and verify that they are valid, or try to break them and understand the guarantees. And if you want to put it on a mainnet and secure billions of dollars, you need something that is very secure and trusted by the research community and everybody. I think that's the main reason why there was no work on quantum security when the Berkeley work started a couple of years ago, because there was no good functions, or they were not good enough that were trusted enough. And even the unified binary trees approach is sort of like, okay, we cannot ship this on the mainnet in the next 1.5, 2 years. And by that time, we are actively working with researchers to prove that Poseidon, or whatever we are going for, is actually the good. Like that's one of the challenges of unified binary trees. Not so much about how the structures look like, but all the other like security properties of it, etc., how fast it's going to be, how performant it is, etc. So there are a lot of aspects to it. And yes, creating the proofs and how long it takes to create the proofs is also a big factor of which kind of function you're going to use. And I don't know all the properties of all different stuff. So the researchers are considering different functions. I don't know exactly which one, how exactly they work, what are the trade-offs between them. Not really my core expertise, but I know that how long certain functions are being known and how well they'll be tested by research community and accepted that they be trustworthy is a big factor they are considering. So yeah, that's kind of my answer. All right, any other questions? Thank you.